Good day and welcome to part one of our discussion on L'Hopital's rule and indeterminate forms. In this video, we're going to investigate what we will think of as a new limit law, L'Hopital's rule. And to motivate L'Hopital's rule, let me recall a limit we investigated in Calculus 1. That would be the limit as x approaches 0 of sine x over x. And when we encounter this limit in Calculus 1, the approach that we would need to evaluate it is very geometric in nature, and it takes probably a page or so of work. So typically my approach in the classes I teach is I just tell students the value of this limit. And we go with it, and I tell them later on when you're in Calculus 2, there is a more quick and efficient explanation as to where that limit comes from. But let's just think about this from a very intuitive perspective. If we want to evaluate the limit of a quotient, we can think individually, what does the top and the bottom go to? So for an input close to 0, a limit explores what are the outputs of this function becoming close to. When x is close to 0, if you just think of the sine curve, sine is getting really close to 0. When x is close to 0, x is getting close to 0. And this leads to something we refer to as an indeterminate form. 0 over 0 has no meaning associated with it. It turns out it could really be any number. A limit of this form might exist, might not exist. It could be 0, it could be infinity. In this case, the value of the limit turns out to be 1. Let me look at two other motivating examples. The first is the limit as x approaches 1 of 2 natural log x over x minus 1. So once again, thinking about this very intuitively, what does the top approach? What does the bottom approach? So as x gets close to 1, x minus 1, this quantity we have in the denominator, is getting close to 0. And we probably need to remind ourselves what the natural log curve looks like. So graphically, we have y equals natural log x. And remember, it has a single x-intercept, 1. So as x approaches 1, the natural log of x is getting really close to 0. So this is once again one of those indeterminate forms. 0 over 0 is not something that has an associated meaning. Similarly, if we want to think about a limit as we approach infinity, that is, as we substitute in larger and larger values of x, what is this function approaching? Thinking of the top and the bottom individually. When x is extremely large, so is x minus 1. So the bottom is going to infinity. And looking at the graph of natural log, for large inputs, our function just grows indefinitely, which is to say it approaches infinity. And it turns out we have a similar problem. Infinity over infinity is once again something that has no associated meaning to them. If we encountered limits of this form back in Calculus 1, our technique was to algebraically manipulate until we can use our limit laws. Unfortunately, I don't see any obvious algebraic simplifications that would allow us to do our limit laws, which is why we need to build up to L'Hopital's rule. To get to L'Hopital's rule, let me just define for you what we mean by an indeterminate form. So a limit as x approaches a of a function f of x over g of x. And if the limit of the function in the top is going to plus or minus infinity, and the limit in the bottom is going to plus or minus infinity, we will refer to this as being an indeterminate form of type infinity over infinity. And note, it could be the case that the top's going to say positive infinity and the denominator is going to minus infinity. That would also lead to an infinity over infinity indeterminate form. There's also a second type of indeterminate form. More will come later. If the limit as x approaches a of the function in the top is 0, and the limit as x approaches a of the function in the bottom is 0, then this limit is also an indeterminate form. And I will oftentimes abbreviate, and I will use IF to represent indeterminate form, and then later on I will also use LH to represent L'Hopital's rule. So in this case we say that the limit is an indeterminate form, now of this type 0 over 0. And if we can identify that we have an indeterminate form, then we can use L'Hopital's rule to evaluate the limit. L'Hopital's rule tells us the following. If the limit of interest is an indeterminate form of type infinity over infinity or 0 over 0, then the limit can be rewritten as what is hopefully a simpler, easier to evaluate limit. We can simply take the limit as x approaches a of f prime over g prime. So you differentiate the function in the top, divide it by the derivative of the function in the bottom. And I do want to be very careful about a few things. The first observation is that L'Hopital's rule only works when you have indeterminate forms. So each and every time you use L'Hopital's rule, you need to somehow explain or verify that you have indeterminate forms. So I'm going to say you need to verify, and don't worry, it's an easy step, that you have indeterminate forms before using L'Hopital's rule. And typically what that would entail is putting arrows to go with the function in the top and the bottom. So for example, if we had a 0 over 0 indeterminate form, this is the work required to indicate that to me. Furthermore, every time you use L'Hopital's rule, you need to tell me, which we will do by simply placing a small LH above the equal signs. So those things need to be included each and every time we use L'Hopital's rule. So let's revisit our motivating examples and see if we can use L'Hopital's rule to evaluate them. So revisiting our motivating examples, in this first example we said as x approaches 1, natural log is going to 0, and x minus 1 is going to 0. That indicates to us that we have an indeterminate form of type 0 over 0. So we can apply L'Hopital's rule, which we indicate by simply placing this small LH above the equal sign. L'Hopital's rule tells us that we take the limit as x approaches 1, we take the derivative of the function in the top, and we divide it by the derivative of the function in the bottom. And then we start over again. We have a new equivalent limit. Can we evaluate it? Simplifying the integrand ever so slightly, this is a limit as x approaches 1 of 2 over x. So pause your video, give yourself 15-20 seconds, tell me the value of this limit. And in this case, the value of the limit is simply 2. And the reason the value of this limit is 2 over x is a rational function. It is continuous everywhere it's defined. So as long as x is not equal to 0, you simply substitute that value in. That's the point that we are trying to get to. So this final step, we took the limit. Let's go ahead and investigate the remaining example. As x goes to infinity, recall the natural log of x goes to infinity, x minus 1 goes to infinity. Indeterminate form of type infinity over infinity. This allows us to apply L'Hopital's rule. L'Hopital's rule tells us we take the limit as x approaches infinity, and we differentiate the function in the top, and we differentiate the function in the bottom. So now it's the limit as x approaches a of 2 over x. Once again, I would like you to pause the video for a moment and tell me the value of this limit. And intuitively, we can say dividing 2 by something really big and positive gives you something small. So note that intuition. Dividing by something big gives you something small. So 0. Which you could also note graphically if you sketch the graph of y equals 2 over x and ask for large positive inputs, what is that curve approaching? It's approaching 0. And the graph in blue is for the function y equals 2 over x. So this completes our introduction into L'Hopital's rule. In our next video, I'll give a small explanation as to maybe why we could expect this to be true, at least a little bit of intuition, and then we'll investigate some examples that turn out to be, a smidge more involved. So stay tuned and take care.